Navigation intimidates many people. The skills and equipment used to navigate a boat safely often seem too complicated and too scientific. But that's not the case. Safely finding your way in a boat takes nothing more than some common sense and simple tools.
I'm John Rumanier. I've done a lot of boating in many different areas, and like you, when I'm out on the water, I'm concerned about my boat's position and her heading. That's what navigation's all about. If you can answer these two questions, where are we and where are we headed, you're a navigator. In this video, we'll look at the basics of modern navigation. Some of the time we'll be on the water, and at other times we'll be using sophisticated simulators in a navigation school at the Seamanship Institute. We'll begin with the basic tools of coastal navigation, with the chart, with the magnetic compass, and with dead reckoning. Then we'll move on to today's electronic devices, radio direction finders, satellite navigation, and finally, radar, which more and more skippers are using. Then we'll talk about navigating in difficult conditions, at night, in fog, and in storms. The equipment that we're using doesn't imply an endorsement. You'll find this gear on boats everywhere. Now, the kind of navigation we're talking about in this tape is the kind of navigation that most people do, which is near shore. It's called coastal navigation, or piloting. While many of these skills will help you sail across the ocean, most people use them to get in and out of harbors and across bays, rivers, and lakes without getting lost and without running aground. Before we get underway, I'd like to stress 3 points about navigation. First, never rely completely on any one single skill or device. Always have a backup. For example, it only takes a couple of seconds to back up a Loran fix or a radar position with a glance at a buoy or at a depth sounder reading. Second, don't be too optimistic. Use a worst-case state of mind. For example, don't regard a fix as an exact small point of position. Rather, regard it as an area of position, the area of your most probable position. And third, be systematic. Write everything down, either on the chart or in a logbook. That way, if you get lost, you can backtrack and find your mistake. With these guidelines, good equipment, and some common sense, you should be able to navigate safely. Before heading out, check that you have all the charts you need, as well as all required safety equipment, including life jackets, fire extinguishers, flares, and navigation lights. Life jackets should be worn by anybody who's not a good swimmer, and by everybody whenever there's a risk of going in the water. No matter how you navigate, with a compass or with a high-tech electronic instrument, you'll need a chart. A chart offers a miniaturized version of the world around you. It helps you make sense of the water and the land. This map for navigators works very much like a road map. It uses colors and symbols to tell you what it is you're seeing around you. White indicates safe, navigable water. Light blue indicates shoal water. Green indicates grass that's sometimes covered by water. Brown is land. Rocks are shown whether or not they're out of the water. And buoys are shown going up into the channel. The colors have been carefully chosen so they're visible under the red lights used in navigation stations, so navigators don't lose their night vision. These symbols and colors are described in this pamphlet called Chart 1 that's published, like the charts themselves, by the federal government's National Ocean Service. In Chart 1, you'll see all of these symbols and colors clearly described. It's a good idea to mark the shoals and rocks in your area with a purple pen that's visible under a red light. Charts come in different scales. The scale indicates the size of the area that's covered. Now, this is a little complicated. but bear with me. Up near the label of the chart is printed the scale. Here the scale is 1 to 20,000. What that means is that every inch on the chart represents 20,000 inches in reality. Here's the rule of thumb. The larger the second number, the smaller the scale. The smaller the second number, the larger the scale. In this case, it's a pretty low second number, so we have a large scale chart. Now, the second rule of thumb is large scale, small area. This is a pretty large scale chart, which means it covers a pretty small area. Most boaters use three kinds of charts: harbor charts, coast charts, and general charts. This chart that we've been looking at is a harbor chart. It shows a pretty small area with considerable detail. You can see how large these islands are on this harbor chart, whereas on this coast chart, here are the same islands. The scale on this coast chart is 1 to 80,000, which is 4 times the scale of the harbor chart we were looking at. Now, on a general chart, the detail is much less. This general chart covers Canada all the way down to North Carolina. Here's the area covered in the coast chart that we were looking at, and these dots are the islands that we've been looking at in the harbor in the coast charts. Now, besides scale, you should be aware of a couple of other numbers that are important. One is the chart's publication number. Each chart has its own number, and it's issued in a catalog. Second, each chart is periodically updated, and the date of the update is published in the lower corner of the chart. You should always have the most recent edition of a chart, or you should correct the chart. Now, it's important to have a recent edition because a ship may have sunk, a buoy may have shifted position, or a storm may have kicked up a shoal area that wasn't there before. There are various ways to update a chart. The most valuable way is to use a publication called Notice to Mariners and another publication called Local Notice to Mariners. Both are issued by federal agencies. Local Notice to Mariners can be ordered from your local Coast Guard district. In these publications are corrections of areas and buoy positions. Sometimes they'll publish small chartlets like this that can be pasted in over the relevant area on the chart. Make sure your boat's inventory of charts covers all the areas where you'll be boating, and especially the harbors. Don't skimp on charts. They're your best insurance policy if you use them properly. You'll need them on deck, but keep them dry and keep them from blowing away. Down below, either roll them up or store them flat under bunks. A convenient and usually economical way to buy charts for your boating area is to get a collection of charts like this chart kit. Be sure to buy the most recent edition. These collections include charts of various scales, and they also show courses. Be sure to check these courses carefully. Many cruising guides and other publications carry sketches of harbors and other areas. Those sketches are no substitutions for charts. Since we need all the help we can get out there, the government publishes some helpful publications, including the Light List, which is a list of all lighted buoys and lighthouses, the Coast Pilot, which is a guide to boating areas all over North America, and for saltwater areas, tide and tidal current tables. If you go out in tidal areas, you want to know when tides change using a tide book like this one, and you'll want to know the direction and the force of tidal currents using this chart. As a general rule of thumb, you should never enter an unfamiliar harbor without having visually inspected the harbor and without having close at hand a detailed chart of the harbor. One of the best aids for the harbor is a good pair of binoculars. Now, binoculars are known by two different numbers. These are 7 by 50s. The first number refers to the magnification. Generally, if you magnify more than 7 times, the horizon and other objects get too bouncy. The second number indicates the amount of light that's picked up. A 7 by 50 binoculars will pick up more light than a 7 by 35 binoculars, so it's better for use at twilight and sometimes at night. Today's electronic navigation devices are marvelous instruments, and we'll talk about them later. but we must acknowledge that they can break down. And if only for that reason, every navigator must know the basic skills of dead reckoning navigation, or navigating solely by the compass and the chart. Dead here means deduced. You deduce your position from observations. Some of the most important of those observations come from the magnetic compass. By constantly orienting the navigator to north, the compass provides the same steady, unchanging frame of reference as the chart. This frame of reference is the Earth's magnetic field, which makes the north arrow in an accurate compass point just to the side of the geographic North Pole to an area in far northern Canada that's called magnetic north. The difference between the direction to the geographic North Pole and the direction that the compass's north arrow points is called variation. The variation is different all around the Earth, and it changes very slightly each year. The local variation is shown on the chart in a miniature of the compass called the compass rose. It's a circle showing all 360 degrees in the compass. Notice that there are two circles, one inside the other. The outer circle shows true degrees, as oriented to the geographical North Pole and to the chart's longitude and latitude lines. The inner circle shows degrees in magnetic measurement, as oriented to the Earth's magnetic field. The inner rose mirrors the boat's own magnetic compass. The variation is labeled on the inside of the rose. To get back to the compass, notice that the degrees are marked on a circular sheet called a card, which is magnified by the compass dome. The card should stay still while the boat turns. If the card moves, the pivot point is worn and should be replaced. A good test is to abruptly stop a boat's turn, and if the card keeps going and lags behind the boat, the pivot needs replacement. There should be no air bubbles in the oil in the dome to obstruct visibility. Keep the dome filled with special oil. A professional compass adjuster will be able to make repairs. A common error on a magnetic compass is called deviation. It's an inaccuracy that's caused by metal and electronic objects that are on board. The object might be as small as a pair of pliers and as large as the engine. To see if you have deviation, run up and down a charted course. If the compass course differs from the charted course, there's an error. You can try to correct for deviation by adjusting magnets in the compass, but better yet, hire a compass adjuster to come on board. Around the compass card are short poles called lubber's lines, which highlight important compass readings and make it easier to steer and take bearings, which means to take a compass direction on another object. There are two ways to steer a course. You can be guided by a permanent object on shore, or you can steer by a number on the compass. In either case, have a chart close at hand and steer into safe water. When you steer by a compass, the compass course is the number directly under the forward lubber's line.
This is a good place to talk about the navigation rules, which we usually call the rules of the road. There are special rules for boats under sail and other rules for boats under power. Boats under sail usually have right-of-way over boats under power. The exception is large power vessels in areas where they don't have much room to maneuver, like narrow channels. Otherwise, the powerboat must give way or stay out of the way of the sailing vessel. In this case, the sailboat is the stand-on vessel, which means she must hold her course so as not to mislead the other vessel. When sailboats meet, three rules apply. First, the boat on starboard tack, with the wind coming over her starboard side, is the stand-on vessel. The port tack boat must keep clear. Second, the boat to leeward or downwind of the other boat is the stand-on vessel. The windward boat must keep clear. Third, a boat that's being overtaken by a faster boat is the stand-on vessel. The overtaking boat must stay out of her way and must keep clear. When boats under power come together, the inland rules of the road, which govern almost all U.S. waters, require that they show their intention by exchanging horn signals and, at night, light signals. When two powerboats meet and must take evasive action, each should turn to starboard while sounding one horn blast in order to signal a turn in that direction. If turns to starboard will not succeed in avoiding a collision, turn to port, making two horn blasts to signal your turn. If you intend to go astern, sound three horn blasts. If you are confused about the other boat's intentions and believe a collision is imminent, sound the danger signal of 5 or more blasts. Now, the inland rules require that the other boat acknowledges your signal before you make your turn, using the same signal that you gave. For example, I plan to turn to starboard should be answered with, I understand, go ahead. However, if the response to is, meaning I'm turning to port, then both boats should sound the danger signal and stop to find a better way to proceed without running into each other. When a powerboat overtakes a slower powerboat, use horn signals to indicate intentions. I plan to turn to starboard and pass you on your starboard side. Or, I plan to turn to port and pass you on your port side. Or, I plan to go astern. The overtaking boat must not make her move until the lead boat acknowledges with the same signals. In crossing situations, the give-way vessel is the boat on the other boat's port side, or left-hand side. The rule is, the boat to the right is right. As in the other situations, the give-way boat must signal her intentions before turning, and the stand-on boat must signal her agreement with the same signal. There's an easy way to tell if a crossing situation might lead to a collision. Take a bearing on the other boat using the compass every 30 seconds or so. If the angle doesn't change, you'll run into each other. Even if you're the stand-on vessel, take evasive action.
The international rules, which govern offshore and in most of the rest of the world, are very similar to the inland rules. The main and most important difference is that there are no intent acknowledgement signals.
Remember that under both sets of rules, at night you must use light signals in the same patterns as sound signals. Near shore, a boat is usually guided into safe water by a navigation buoy placed by the government to indicate deep water. Under the lateral system of navigation in North America, as you enter a harbor, the left or port-hand side of the channel is marked by green and black buoys, which have odd numbers and may have green lights, while the right or starboard-hand side is marked by red buoys with even numbers and sometimes red lights. The center of the channel, or the area of deep water, may be marked by red and white buoys with a white light at the mouth of the harbor. When you steer by the compass, don't stare at it. You'll be mesmerized. Rather, keep your eyes moving from the compass to the horizon, to the clouds overhead, to the engine controls, to the sails, back to the compass, and so on. And don't try to steer too precise a course. If you can steer within 3 degrees of the given course, you're doing very well. Using a compass course and chart allows you to plan your course so it doesn't take you into shallow or dangerous water. First, on the chart, locate a nearby charted object in safe water, like a buoy, to serve as your point of departure. From here, draw a light line through safe water to your destination or to a turning point. This line is called the intended course. Now you must figure out the compass direction of this line. This is the course to steer, or your heading. The direction is in compass degrees, or magnetic degrees, the same degrees that are on the inner circle of the compass rose on the chart. Some navigators like to refer to the outer circle and true degrees, since the grid of latitude and longitude lines on the chart is oriented to true north. They convert a true direction to magnetic direction by adding the variation if it's to the west and subtracting the variation if it's to the east. However, I think that using true degrees invites confusion. What if you make a mathematical error? What if you fail to convert from true to magnetic? Still, if you want to use true degrees, go ahead and do so, but be sure to distinguish between true and magnetic, both in your own mind and when you communicate with your shipmates. Now, there are several ways to calculate courses. Two of the most popular ways are to use a parallel ruler and a plotter. In all the examples in this video, we'll be using magnetic degrees. With parallel rulers, you place one edge along the line and then walk the rulers across the chart to the center of the compass rose. Read the heading on the inner circle in the direction in which you're going. Errors are always possible, so double-check your work. Don't set courses that are so precise that they can't be steered. For example, a course of 242.5 degrees is impossible to steer. Better, set a course of 242 or 243 degrees. With a small compass, it's best to set courses in the 5-degree increments shown on the compass card. If you must err, do so in the direction that takes you into deeper water or that takes you upwind. For example, here, 240 degrees would be a good course. Once you're on this line, it's called the track. To keep a record, you should label the track with your course and speed. C indicates course, M indicates magnetic, T indicates true, S indicates speed, K indicates knots, and MPH indicates miles per hour. Speed can be estimated, or it can be read off a speedometer. Draw an arrow to indicate the direction you're heading. That's how the parallel rulers work. A plotter is a protractor with an arm. First, adjust the protractor to match the local variation as shown on the nearest compass rose. Here the local variation is 13 degrees. Adjust the protractor and tighten the set screw. Remember, since local variation changes every few miles, you may have to reset the variation as you go down your track. Orient the protractor on the nearest latitude and longitude lines and lay the arm over the track. Read the course on the protractor and then label the track as we did with the parallel rulers. 242.5 degrees. It's always a good idea to write down in the log your point of departure, your course, and your speed. This is called making log entries, or logging in. On a passage of longer than several hours, log entries should be made regularly, say every 30 or 60 minutes. Another way to calculate courses, it's a quick and dirty way and not very accurate, is to lay the side of your hand along the track and then slide it carefully across to the compass rose. It's a way to get a quick course when you're navigating in the cockpit. When setting the course, make sure you compensate for wind or current that may drive you off course as much as 5 or 10 degrees, right down on rocks and buoys.
When the land appears to move beyond a stationary object, like this anchored lobster pot buoy, the current is pushing you to one side.
A good way to check for side slippage is to steer toward a range made up of 2 stationary objects, one behind the other. Preferably they should be 2 landmarks on shore, but if pressed, you might choose a buoy and a landmark behind it. If the 2 objects stay in line, you're holding your course. But if they go out of alignment, you're being pushed to the side and must compensate. Here's a neat trick for predicting how far you'll be set by the tide. Check the tide tables to see how the tide will affect your boat. For example, if you're out in the 2-knot current for 3 hours, you'll be affected a total of 6 miles. If the current's from behind, it will speed you up. If it's from ahead, it'll slow you down. But if it's from the side, it will set you off your course by 6 miles. How do you know what course to steer to compensate? An easy guide is the rule of 60. Multiply the distance you expect to be pushed by 60, and then divide the product by the distance to your destination ahead. The result is how many degrees you should alter course into the current in order to compensate. For example, if you think you'll be pushed 6 miles to the side and your destination is 20 miles ahead, you'll have to alter course 18 degrees into the current. All right, you set your course and you're going down it. You're somewhere on that track, but where? If you know how far you've gone, you can deduce your position. Some boats have odometers called logs, and other boats have speedometers. If you can estimate your average speed over a known period of time, you can calculate how far you've gone. That distance is called the distance run. If you don't have a log, use a couple of tricks for figuring distance run. One is called the 6-minute rule. Plot your position every 6 minutes, or every multiple of 6 minutes. Since 6 minutes is 1/10 of an hour, every 6 minutes the boat goes a distance equal to 1/10 their speed. That makes calculations easy. Another trick is to use a simple formula called the speed-time-distance formula. Multiply your average speed by the amount of time in minutes that you've been underway and divide the product by 60. The result is the distance you've run. For example, if you've averaged 6 knots for 25 minutes, you've run 2.5 miles. Another way to calculate distance run is with a time-speed-distance calculator, which is essentially a circular slide rule. Turn to the time, which is 25 minutes. Then turn to the speed, 6 knots. And read the distance run on the outer scale. Here it's 2.5 miles. On many charts is a logarithmic scale that can be used to solve for distance, time, or speed, as long as you know the two other factors. All you need is a pair of dividers. If you know how fast you've gone, for how long, you can solve for distance run this way. Put the right leg on the end of the scale and the left leg on the number corresponding to the speed. Then, without changing the dividers, put the right leg on the time. Under the left leg will be the distance. On the Great Lakes and the major rivers, the distances are in statute miles and the speeds are in miles per hour. On salt water, the distances are in nautical miles and the speeds are in knots, or nautical miles per hour. A nautical mile is 1.15 statute miles. Now that you've calculated your distance run, you can plot your position. With your dividers, using the mileage scale on the chart or the latitude scale parallel with your position, spread the legs until they cover 2.5 miles. Then put one point on your departure point and another on the track until it just pricks the paper. Draw a dot on that point and a half circle around it and write the time. That's your deduced position, usually known as the deduced reckoning or dead reckoning position. This is abbreviated DR. It's based only on the boat's heading or course and on the distance she's gone, or the distance run. The symbol of a DR is a half moon over a dot. If you don't know your speed, use another version of the speed-time-distance formula to calculate it. Time your run along a known distance, say between two buoys that are charted, and enter it into this formula. With this information, you'll be able to calculate dead reckoning positions later when there might be no buoys around. A DR is a position deduced from only 2 observations. Now, the speedometer might be wrong, or you may not have steered the course that you recorded. So you shouldn't treat a DR as a precise point. Think of it as a general area. Yet while you should think of a DR with caution, it can be a very helpful check against positions arrived at otherwise. Use any observations that you can, any sort of information. If you have one other piece of information, you can use it to estimate your position. An estimated position is called an EP. For example, you might be right near an island. Mark an EP with a small box. A reading from a depth sounder may give an EP if the reading is strikingly deeper or shallower than nearby readings. Remember that depths shown on the chart are for low tide. Depth contour lines are shown on charts to indicate points of equal depth. Using the depth sounder, you can follow one of the contour lines, for example, to stay outside this reef. The best bit of information for estimating a position is a compass bearing taken on a charted object. This produces a line of position, an LOP. You're somewhere on that line. You can take a bearing on any charted object that's above water. The best ones are stationary: lighthouses, water towers, smokestacks, and so on. Buoys are not too reliable since they swing in the tide and wind, since their anchors may drag, or since the Coast Guard may shift their position. Sometimes, however, only buoys are available. The bearing, or line of position, is the compass direction from the boat to the object. It can be made over the main compass, Sight the object down your index finger, then drop your hand onto the compass and read the number under your fingertips. Another way to take a bearing with the main compass is to steer directly at the object and read the bearing off the forward lubber's line. A more accurate way to take a bearing is to use a hand-bearing compass. Some are high-tech versions of the old Boy Scout compass. This one is nicknamed a hockey puck because of its appearance. This is a flux gate hand-bearing compass. It must be held parallel to the water to take an accurate reading. It has a digital readout and a memory. On the chart, plot the bearing line. First, place the parallel rulers over the number on the inside circle of the compass rose. Then slide the ruler up to the charted object until it crosses your track. Then draw a light line to the object across the track and label it with the bearing and the time so you know what the position was based on. Use an arrow to indicate which object was sighted and mark your EP with a small box. Note the time of the bearing on the chart using the time scale of the 24-hour clock. An estimated position is generally more reliable than a dead reckoning position. However, if you take 2 or more accurate bearings and cross them, you have an even more reliable position called a fix.
There's the stack. Okay. I've got a bearing on it. It bears 034 degrees. We've got the lighthouse right here, too. I've got a bearing now. The lighthouse bears 330 degrees.
The best bearings cross at angles of 60 to 90 degrees to each other and no less than 30 degrees to the boat's course. That way, any errors will have small effect. Plot and label the bearings. Mark their intersection with a circled X. That's the symbol for a fix. Be sure to note the time of the fix. It's often helpful to take a third bearing. If one is way off, double-checking may indicate that you should throw it out. But if the bearings all cross each other very nearby, you have a good fix, and you can consider yourself near that triangle. To repeat, don't think of a charted position as an exact point, but as a small area of position. Keep such hazards as rocks and shoals well outside that area. Plot your positions regularly and before every course change. Since you're keeping track of your positions on the chart, there's no reason to log every one of them. But you should make a log entry on a regular basis, more frequently in bad weather. Also make a log entry whenever you change courses. Now that we've covered the basics of navigating by compass, we can enter the world of electronic navigation instruments, some of which use exactly the same concepts and all of which ultimately depend on charts and compasses. The simplest of these instruments is the radio direction finder, or RDF. You use it by taking bearings on charted transmitters called beacons, by homing in on their signals, and calculating compass bearings to the transmitters. The advantage of an RDF is that it may be effective 30 to 200 miles from the transmitter. Compare this with the short range of a bearing taken by sight. The disadvantage is that RDF bearings usually are not as reliable as good sighted bearings. Plan for an error of 5 to 10 degrees. To operate an RDF, first find a nearby beacon on the chart. They're labeled with purple circles, with the radio frequency and the call sign in Morse code. Many beacons are in lighthouses. Lists of beacons are often carried in tide tables and other publications. The modern handheld RDF can be aimed right at the beacon, like a hand-bearing compass. First, get the boat on a compass course that's as steady as possible. Tune the receiver to the frequency of the beacon and listen for the radio signal through earphones. Turn the device until the signal disappears. That silence is called the null. Then read the bearing off the dial on the device. To make an estimated position or fix with RDF, plot and label the bearings as you would bearings taken with a compass. Add the notation RDF or RBN so you know what kind of bearing it is. Of course, you can cross an RDF bearing with a compass bearing. The Seamen's Church Institute has been serving the spiritual and professional needs of mariners for more than 150 years. We're in the simulated bridge in its navigation school to look at electronic navigation instruments.
Today, GPS is the system of choice in electronic navigation. GPS, Global Positioning System, is a worldwide navigation system that uses an instrument picking up signals from more than 20 satellites that rotate the Earth twice a day at a height of about 12,000 miles. Acquiring signals from several satellites, the instrument's computer triangulates them to provide extremely accurate positions. Using the latitude and longitude coordinates, plot your position on the chart. The instrument can also calculate your boat's course, speed, and other helpful information. If you program your destination or other locations as waypoints, the instrument will compute and display the course and distance to them, and even the time remaining before your arrival based on your current speed. The main trouble with GPS is that it's an electronic system. If it fails, you must be able to fall back on dead reckoning navigation. On some GPS instruments, information is displayed graphically on small maps. These maps are no substitute for up-to-date nautical charts. Some GPS instruments are large and permanently fixed below, with their antennas on deck, while others are hand-held. Each instrument has a unique design, but all have multiple functions that can be displayed by pressing the buttons. Since no navigator should ever rely solely on one type of navigation, be sure to double-check your GPS positions by dead reckoning or coastal piloting using your charts, and especially by keeping a sharp lookout.
One of the oldest electronic navigation devices is radar. It's also one of the best for navigating near shore. Radar is now available in surprisingly compact and inexpensive packages for small and medium-sized boats. Before I go on, I'd like to say that while radar has some wonderful advantages, it's more difficult to use than other navigation equipment. If you use it correctly, it will keep you out of trouble. But if you use it and interpret it incorrectly, it might lead you into trouble. People who purchase radar receivers should be aware that their legal liability in case of a collision may well depend on proof that they have accurately interpreted the radar display. Courts have ruled that skippers who do not properly use or interpret radar can be guilty of culpable negligence. In other words, use your radar properly and also take into account all other kinds of information that's available. According to the navigation rules, Rule 7, risk of collision, Proper use shall be made of radar equipment if fitted and operational, including long-range scanning to obtain early warning of risk of collision, and radar plotting or equivalent systematic observation of detected objects. It may well be that the only way you can convince a judge that you've used your radar set properly is to show a certificate of completion of a radar observer's course. In this video, we can't tell you everything about radar. That would take an entire video or more. But we can provide some rules of thumb for interpreting the information on a radar scope. A radar set works by sending radio waves out through a rotating device called a scanner. The waves bounce off objects, which are usually referred to as targets, and then back to the set, which then converts them into readings on a screen called a scope. The radar we're looking at is what's called a relative motion unstabilized radar. Another way to describe this kind of radar is head up or bow up. What we see up the line is what we would see over the bow of our boat. This means that when the boat turns to the east or to the west, the land is not oriented in the same way it is on most charts. Objects and targets on a scope are shown as pips of light. When you first look at the scope, determine what the range is. It's shown by a number somewhere on the scope. Most radar sets have various ranges that you can set. Here it's 12 miles. That's the distance that's represented from the center of the scope to the perimeter. The center is where we are. We'll shift down to 6, and then to 3 miles for a much smaller area. Once again, we're located in the center of the scope. This line is the heading line. That's our course. This is a head-up type of radar. And the pips of light represent many objects. Here we have some buoys, land, up to the top, a large mass of land, some islands. Here's the Greens Ledge Lighthouse right here. Here's another buoy. And here's a boat or a ship working her way in this direction. Now you can identify and position objects on the chart using two different measurements. One of them is called the electric bearing line. It's an adjustable dotted line, as you can see here. I'm adjusting with a knob, that you can have cut right through one of the objects. It shows the relative bearing off the bow, and the bearing is shown in the bottom left-hand corner right here. The electronic bearing line shows relative bearing off the starboard bow. You add it to your magnetic course to determine what the magnetic bearing is. The other way is by determining the object's range or distance from you. The scope has rings like this that are at equal intervals from your position out to the perimeter. In this case, they're every half mile. In addition, there's a device called a variable range marker, which can be adjusted with this knob. It's that circle, that dotted line. It can be expanded out to the target. And you can read the range in the bottom right-hand corner. Here, the range is just under 1.5 miles. So we can position this target. We know that it bears 62 degrees off our starboard bow and that it's 1.46 miles away. Radar has a number of distinct benefits, most of which are not available with other kinds of electronic equipment. With a properly tuned radar transceiver, our crew has a new pair of eyes to peer beyond the horizon through most kinds of weather. On a pleasure boat, the geographical range of these eyes is about 20% beyond the horizon. These eyes can see in daylight, night, or fog, but they can't see in rain, since precipitation causes considerable clutter. These eyes can take reliable bearings on and accurate ranges to other objects. The first of the skills available with radar is weather forecasting. Since rain shows as a dense cloud on the scope, you can track rainstorms. Second, a radar can be used while navigating at night or in fog by finding unlighted navigation buoys, many of which have radar reflectors or are especially designed to reflect radar signals very effectively. Third, you can use radar to find your position. Once you've identified a lighthouse or a landmark on or offshore, take a bearing on it and determine its range. Those two measurements together provide enough information for a pretty reliable fix using only that one object. To convert the radar data to a charted fix, first locate the lighthouse or landmark on the chart. Read the chart carefully. Not only is its scale very different from the radar's scale, but it may be oriented in a different direction as well. To be able to use the relative bearing, you'll have to convert it to a magnetic bearing. Here the relative bearing is 009 degrees, and our heading is 340 degrees. Add 009 to 340, and you come up with a magnetic bearing to Green's Ledge Light of 349. So let's plot it. Lay off a light line. Now the range is 2.6 miles. Lay that off on the latitude scale. 1 mile, 2 miles, 2.6 miles. And with this drawing compass, put the point on the light and draw an arc across the bearing. Where it crosses is a fix. Label that a radar fix. You can also take ranges on 2 or more charted objects. Your position is where the ranges cross. Using ranges is more reliable than using radar bearings. Just take ranges on 2 or more objects. Once you've taken the ranges, use a drawing compass to plot the fix on the chart. Where the ranges cross is where you were when you determined the ranges. The fourth way that radar is used is to avoid collisions with other boats. This is the way that most people use radar. This is a fairly typical situation here. We're in the center, headed in that direction, and around us we see a variety of objects. Some of them are stationary and some of them seem to be moving. To find out if they're moving toward us, we can use 2 instruments. First, the rings that show the range to the objects, and secondly, the electronic bearing line. If the bearing stays the same, we're going to have a collision. We watch the situation as it develops. We see if the other vessels get closer to us, and we also see if they stay on that same bearing. Now we have to remember that we're moving as well as they are, so the motion that we see is relative motion. We have to take our own motion into account. Notice here that we're moving away from this small pip right here. That indicates that it's a buoy that's stationary in the water. However, these 2 objects seem to be moving in this direction, and they seem to be moving on the same course at the same speed. That indicates that they might be a tow with a tug pulling them ahead. Notice how the second object is quite a bit larger than the first object. In situations like this, try not to be distracted by events on board. Keep your concentration on the radar scope and on the water around you. The most thorough way to interpret a radar scope is to keep a careful plot of what you see on it. This is how professional mariners and Coast Guard radar observers use radar. In plotting, which is done either on paper or in grease pencil on the scope of the radar, you do a vector analysis of the other boat's maneuvers to see if its course will intercept your course. It's a special skill, and it needs some training at navigation schools like this one. But for the average boater, you can do very well with a straight edge, which you lay over the course of the other vessel to see if it will intercept you. The average boater will do best to observe the targets. If the range decreases and the bearing remains constant, as here, a risk of collision exists. But if there's no risk of collision, Lay a straight edge across the pips as they move across the scope. This way you can determine the closest point of approach between your boat and the target. If this seems confusing, remember that you are moving as well as your target. What should you do if there's a risk of collision, and how do you avoid collision? Obviously, you're going to have to alter course. The navigation rules are very specific about the obligations of boats in this situation. When you alter course, you must alter course decisively. Rule 8 says, any alteration of course and/or speed to avoid collision shall, if the circumstances of the case admit, be large enough to be readily apparent to another vessel observing visually or by radar. A succession of small alterations of course and/or speed should be avoided. Tell the other vessel your intentions. The rules specify that certain light and/or sound signals be used. It's a good idea to talk to the other boat over the radio. Identify yourself clearly. Describe your course and your intentions, and ask for an acknowledgement. Now let's see how a navigator brings together radar, the chart, and on-the-water observations to enter a tricky harbor. Here's the first part of the approach as it's seen on the radar scope. Remember, the boat's at the center, and the white line shows her heading, or the view over the bow. In the upper left-hand corner is the range. Here it's 1.5 miles. We're heading north, and we'll turn east around the lighthouse and around the shallow water marked in blue on the chart. On a dull day like this one, or in the evening or early morning, buoys and lighthouses don't appear in much detail. Sometimes all you can make out is their outline. That rocky foundation is called riprap. Stay well clear of it. As the boat turns on a head-up radar display like this one, the heading line stays vertical while the land rotates. This orientation is different from the north-up chart display. Notice how the land seems to blur. Approaching the channel, we search on the scope, the chart, and the water for buoys that will guide us using the rule red, right, returning. In poor light, buoy colors can be pretty bland, but you can tell a can by its flat top and a nun by its pointed top. We move into the channel searching for the pair of buoys, green to port and red to starboard, that define the channel edges and guide us to safe water. Buoys may be small and hard to see. Here a powerboat comes out of the harbor through the channel right at us, and we turn to starboard to pass port side to port side as the rules prefer. We keep moving up the channel, switching to shorter ranges in order to get more detail in the scope. Two problems with short ranges are that you lose the geographical context and that the land is very blurred. Switch back and forth between short ranges and long ones to get both detail and context. Radar doesn't see everything. Low, flat objects like this marshy island won't be picked up by radar. The best targets are vertical and have hard edges. Hang a radar reflector in your rigging so you're visible to the radar sets on other boats. With a radar detector like this one, you can estimate the direction to other boats that have radar sets that are on. This alarm will tell you when they're nearby. While radar may seem simple, it's actually rather complicated, partly because there's so much information on the scope, and partly because the observer is in motion. Navigating when the sun is down or obscured, or when a storm is brewing, takes some experience, but it's not impossible. It's important not to rely exclusively on electronic devices. Keep your eyes open and use the wide array of tools and skills that we've discussed here. Lighthouses and lighted buoys show distinctive colors and distinctive patterns. Green lights indicate green or black buoys that must be left on the port hand when entering a harbor, while red lights indicate red buoys that must be left to starboard. White lights show the middle of channels.
Most buoys have reflectors that make them visible under the beam of a bright flashlight.
Some lighthouses show a warning light known as a red sector. A section of the light is red and is shown over dangerous waters and land. If you're in the red sector, you're in trouble. At night or in bad visibility, say in rain or fog, it's safer to steer from one lighted buoy to the next one, hopscotching down your course. Good seamanship requires that in these dangerous conditions, speeds be kept low and that an alert lookout be posted. If you aren't using waypoints on a low-RAN-C receiver, you can use our old friend, the speed, time, distance formula, to help you get from buoy to buoy in very bad visibility. For instance, in thick fog or in a rainstorm. This is called running out your time. If you know the distance between the buoys and know your speed, you can determine how long it will take in minutes.
You can also make these calculations on the chart's logarithmic scale or on a speed, time, distance calculator.
The trickiest part of taking bearings at night is making sure you know what it is you're looking at. Lighted buoys with the same color lights have slightly different timing, called phase characteristics. Some lights flash every 2.5 seconds, others every 4 or 6 seconds. Look at a light for a while and either use a stopwatch or count 1001, 1002, 1003, and so on to determine its characteristic. Double check yourself. What looks like a dark period may be a passing boat or a wave coming between you and the buoy. Use lighthouses whenever possible. They don't change position, and they're visible for long ranges. They're also easier to see. This is partly because they're higher off the water. The chart label for a lighthouse includes a height in feet, which is the height of the light above the low tide level. Another number is the range of the light in miles. On a clear night, the light should be visible within that range. On an overcast night, the range may be greater since the light is reflected by the cloud cover. A radio direction finder can be a great help in these bad conditions. Use it to home in on a harbor that you're approaching in fog or at night. Just tune the receiver to the transmitter at the mouth of the harbor so the null is dead ahead, and steer so that there's always a null. If you hear the Morse code signal, you know you're off course. Familiarize yourself with the lights of different ships and boats, which can look very different at night. When you see red and green lights, the other boat's heading directly at you. If you see the red light, her port side is to you. If you see her green light, her starboard side is to you. If you see a white light alone, that means the boat's going away from you. You're looking at her stern. The color of lights and their combination indicate the type of vessel that you're near and her heading. When you see a red or a green side light with no white light above it, you're looking at a sailboat under sail. If you see a colored side light with a white light well over it, that's a sailboat under power. Here we see a tanker crossing us with her starboard side to us. The white light on her bow and the top white light aft are masthead lights, commonly called range lights. Here's a large tug pulling a very long tow. The upper range light is just to the right of the lower one. This tells us that we're looking at the tug's port side. This will be a close crossing with each vessel on the other's port side. This is a tug pushing a barge. This and our discussion of the rules of the road are meant as overviews. For a thorough description of navigation lights and rules, see the Coast Guard book, Navigation Rules, International Inland. When a squall or gale threatens, you should attend to some basic navigation requirements before things get out of hand. First, fix and plot your position as accurately as possible. Second, if you can't get into a safe, protected harbor immediately, go out into open water as far from land as you can so you won't be blown ashore. Calculate and write down the courses that will take you to deep water. If you practice with your compass, charts, and electronics, you should develop the confidence and skills to handle your boat safely in normal conditions. However, there are conditions when all these skills and all this equipment will not offer the accuracy and security that you need for safe navigation. The skipper and navigator must use common sense, the weather forecast, and an honest evaluation of their and their boat's strengths and weaknesses to help them decide if and when they should go out on the water. In the end, the ultimate responsibility for safe boating is skippers.